Welcome to the Mechanics of Solids lecture series. In this series of videos, we're evaluating shear in built-up beams as it pertains to connection design. Our lesson objectives are to evaluate horizontal shear stress and shear flow across the connection interface of built-up beams. Then we can design the connection interface of a built-up beam by specifying required glue strength or weld strength or bolt strength and spacing to transmit the required shear. The first example that we'll look at is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. The problem statement reads, a wooden beam is fabricated by bolting together three members as shown in the figure, with cross-section dimensions as shown. The 8 mm diameter bolts are spaced at intervals of s equals 200 mm along the x-axis, and this picture here illustrates the spacing of the bolts along the length of the beam. If the internal shear force in the beam is V equals 7 kilonewtons, determine the shear stress in each bolt. So let's go ahead and denote the given information. Given information is that V, the shear force, equals 7 kilonewtons, and the bolts are spaced 200 millimeters along the beam, and each have a diameter of 8 millimeters. So in order to solve this problem, we need to evaluate the shear flow along the connection interface. In order to do that, we need to evaluate Q along the connection interface. We need to know the moment of inertia, and we need to know the centroid of the cross-section. So we will start by drawing a picture that will allow us to evaluate the centroid. And I draw this picture breaking the section up into pieces that will easily allow us to evaluate the centroid. I may want to look at it differently when I'm evaluating Q. In terms of centroid, I'll call this section 1 and this section 2. Section 1 has a width of 120 millimeters, a depth of 90 millimeters. Section 2 has a width of 40 and a depth of 300 minus 90, or 210 millimeters. Let's just say units millimeters to save us a little bit of writing. We'll need to know the centroidal locations from a reference axis of each of these sections. I'll make the reference on the bottom. The centroid up for 2, which I'll call Y2, is equal to half of 210, or 105. The centroid up to 1, which we can call Y1, is equal to 210 plus half of 90, or 45, which is 255. So now, evaluating the centroid, Y bar equals the area of 120 times 90 times Y1, 255, plus the area of 210 times 40 times Y2 bar, 105, divided by the total area, 120 times 90 plus 210 times 40, which computes to 189.4, and the units are millimeters. So that gives us the location of the centroid, which is 189.4 from the bottom reference axis. Now we'll solve for I using the parallel axis theorem. I equals the moment of inertia of section 1, 120 times 90 cubed over 12, plus 80 squared, 120 times 90, and D for section 1 is 255 minus 189.4. We square that term. Plus I for section 2 is going to be 40 times 210 cubed over 12, plus 80 squared for section 2, 210 times 40 times 189.4 minus 105 squared. And the result for I, truncating significant digits, 144 times 10 to the 6th millimeters to the 4th. Okay? Next we'll evaluate Q, and in order to do that we'll look at the cross-section a slightly different viewpoint. We want to evaluate Q so that we can evaluate stress along these connection interfaces. So we need to isolate the area on the other side of the interfaces. So the area that we'll use to evaluate Q is the area of these two little side sections. Okay? So Q is equal to the area of those side sections, which is going to be 2 times 40 times 90. And then the distance from the centroid, overall centroid up to their centroid, which, if we recall, the distance from the bottom up to that axis was 255. So this distance here, this y that we need for this calculation, is going to be 255 minus 189.4. And that computes to 472,300 millimeters cubed. Okay, so now we know I, we know Q for the section, and V. We can simply evaluate the shear flow. F equals VQ over I is going to be 7 kilonewtons, or 7,000 newtons, times Q, 472, 300 millimeters cubed, divided by I of 144 times 10 to the 6th millimeters to the 4th. This gives us a shear flow of 22.9 newtons per millimeter across the connection interface. The shear flow F is equal to the force in the bolts divided by their spacing. And since there's two bolts across, there's two connection interfaces, two bolts across the connection interface, we're going to multiply this by 2. So we can solve for V bolt as F times S divided by 2, which is going to be equal to the 22.9 newtons per millimeter times the spacing of 200 millimeters divided by 2, and that computes to V bolt equals 2290 newtons. That's going to be the force across each bolt. The very last step, to compute the shear stress across each bolt, we're going to multiply the force, or divide the force by the area. V bolt divided by the area of the bolt. So we take 2290 newtons divided by the area, which is pi over 4, times the bolt diameter, 8 millimeters squared. This gives us a value of 45.6 megapascals for the shear stress across each bolt. And that's the answer to the problem. The units are correct, the values are reasonable, and that completes this example.